Welcome back to our series on probability theory. My name is Mark Ledbetter, and this is lecture video number 9. We're talking about independent events, and so last time we defined events A and B and said that they were independent if and only if the probability of A and B is equal to the probability of A times the probability of B. In other words, and we could also rewrite this as the probability of B given A is simply equal to the probability of B. All right. Now this is an if and only if statement. So if we have independence, that implies that this statement A and B equals the probability of A times the probability of B. If we know that the probability of A and B is equal to the probability of A times the probability of B, then we know that A and B are independent. So if and only if means that it goes in both directions. So in this section, we've already defined the independence of two events. In this video, we're going to give you a definition for pairwise independence and mutual independence. So let's get started. I want to start out with a theorem, though, before we go to pairwise. If two events, A and B, are independent, then A is also independent of B complement, A complement is independent of B, and A complement is independent of B complement. Let's prove the first one of these, and if we prove that, it's very easy to show the others. So recall that probability of B complement given A is equal to 1 minus the probability of B given A. That's the complement rule for conditional probability. Then we have the probability of A and B complement is equal to the probability of A times the probability of B complement given A. This is our multiplication rule, where we don't necessarily know if it's independent. So now we're going to substitute this statement in for here, which makes it the probability of A times 1 minus the probability of B given A. All right. Now, this is equal to the probability of A times 1 minus the probability of B, because A and B are independent. So the probability of B given A is just the probability of B. So that's an aside to our proof. And then we can rewrite this. This is the probability of B complement. So this is the probability of A times the probability of B complement, and this has proved that A and B complement are independent. B and C are similar. Okay, so now let's talk about pairwise independence. And to do this, we start with at least 3 events. So let's say that we have 3 events, A, B, and C, and we say that they're pairwise independent if A is independent of B, A is independent of C, and B is independent of C. So in other words, all the groups of 2 events are independent. Okay? And again, we can as easily extend this definition to more than 3 events. It just means that every pair of events has to be independent. Now, mutually independent events, this goes a little bit further. So A, B, and C are events that are mutually independent if and only if A, B, and C are pairwise independent, and in addition, the probability of A and B and C is equal to the product of their probabilities. Probability of A times the probability of B times the probability of C. And again, this can easily be extended to more than 3 events. So please do not confuse mutually exclusive events with mutually independent events. These are different things. Mutually exclusive can talk about 2 events and they are disjoint. Mutually independent is very different. In fact, a nice question is, what's the relationship between independence and mutually exclusive events or disjoint events? So this is something I'll leave for you to think about. It is interesting. Now let's do an example. We have an urn. It contains 4 balls. They're numbered 1, 2, 3, and 4. One ball is randomly selected from the urn. So let's define these events. A is the event of a 1 or a 2. B is a 1 or a 3. C is a 1 or 4. So let's determine if A, B, and C are pairwise and or mutually independent. So we need to know what the probability of A, now it contains 4 balls. So the probability of A is going to be 2/4 or 1/2. The probability of B is again equal to 1/2. And the probability of C is also 1/2. So now the probability of A and B, that's the intersection. Notice that A and B both have 1, and that's it. So the probability of A and B is going to be the probability of getting a 1, which is 1/4. Now, is this equal to the probability of A times the probability of B, which would be 1/2 times 1/2, which is 1/4? Yes. So A and B are independent. Let's do the same thing with A and C. So A and C equals, again, the 1 is the only thing in common. So this is going to be 1/4, and then the probability of A times the probability of C is 1/2 times 1/2 equals 1/4. So A is independent of C. Now let's look at B and C. So again, the only element in common between B and C is a 1. So 1 out of 4 is 1/4. And then we take the probability of B times the probability of C, and they're both 1/2. So B is independent of C, so A, B, C are pairwise independent. Now finally, to check mutually independent, we have to check that the probability of A and B and C is equal to the probability of A times the probability of B times the probability of C. So again, A, B, and C, they all have the 1 in common, and it's the only thing, so that's going to be a 1/4 for the probability. Then we've already figured out that probability of A, B, and C are all 1/2. This is equal to 1/8. So 1/4 is not equal to 1/8. So A, B, C are not mutually independent events. So let's go to a rocket system now. It says it has a built-in redundant system. In this system, if component K1 fails, it is bypassed and K2 is used. Likewise, if K2 fails, it's bypassed and K3 is used. There's only 3 components in this imaginary rocket. Suppose that the probability of failure of any one component is 0.15. Assume that the failure of these components are mutually independent. Determine the probability that the system does not fail. All right. So the probability that it does not fail is the probability of, let me redo this as probability of A and A1 and A2 and A3 not, or complement. And so this is equal to 1 minus the probability of A1 and A2 and A3. And because, by the complement rule, and then because these are mutually independent, this is equal to 1 minus the probability of A1 times the probability of A2 times the probability of A3, which is 1 minus 0.15 times 0.15 times 0.15 equals 1 minus let's see what this gives me, 0.15 cubed, 0.003375, and subtract that from 1, and I get 0.996625. To 4 decimal places, this is 0.9966. All right, so there we have an example of using mutually exclusive or mutually independent events to calculate a probability, along with the complement rule. So for this lecture, please make sure that you scan in your notes by midnight tonight. Make them neat for you. Again, these are for you so that when you study or you do homework, or if it's open notes test, if you use your notes, then they're easy for you to find and understand. As always, if you have questions, I welcome you at my virtual office hours. If those don't work for you, email me, or if you want some extra time one-on-one, email me. I'm happy to help you. So hope to see you next time, and until then, think probability theory.